I'm just going to start this time by running the demo program, which you see the body of on the left, part of the body of. It's a quite long program. And then we'll talk about what we're seeing. Yeah, I did read. Never mind. I'm not going to go off topic. I'll answer that after the stream. So let me just run the program. And it prints out a bunch of stuff. And what it is printing is a type table that contains a description of every type used in the program, of everything that you could have. So the first type is not in any particularly sorted order, but you look through here and you can see some things like there's a void, there's a bool, there's a string. Here's well, let's take a simpler function. Here's a pointer to a U8. If you haven't been watching these too much, this little caret is a pointer to syntax, and enough Europeans have convinced me that that's a bad idea that it'll probably change in the future, so don't get too stuck on that. The problem is it's a dead key on a few European keyboards, so it's like impossible to type nicely. Anyway, here's a function that takes two pointers to U8s and returns a bool, and etc. Now, what this table is basically just a data structure that gets put into the data segment of your program. And when I run now, I'm just printing out all 94 entries that happen to be, or 95 if we're zero indexed, yeah, that happen to be in my data segment right now. Now, because this contains everything in the statically compiled program, that means that you can talk about all the types in your program using only statically declared data that was put into your data segment at compile time. Now, the amount of data here is about 6 or 7K for all this stuff, kilobytes, and there's not really been any effort to make it small. In fact, things are generally big and unpacked so that your program can access them very easily. If there was a desire to, we could do a compressed format version of it, or, if you're on like an embedded system, and ROM is very precious and you wouldn't want to spend 7K to however big it would be for a bigger program, or if you're just a minimalist and you don't want stuff in your data segment, there's options for that we'll get to later in the talk. So don't be totally turned off by the fact that there's data being put into your program. But what I want to do is start out by showing all the cool stuff you can do when there is data being put into your program, and then we'll insert the other options. So let's just look at the code of what this is doing right now. Exactly. So right now our main is just calling print all types, right? And print all types is saying, hey, the type table has how many entries, right? That's what we saw at the top here. And then it's just iterating over every member of the type table and printing some stuff, just the index, and then calling this other function print type, right? So first, let's look in our this module basic. Is sort of where I throw stuff by default right now. Eventually things will be renamed and namespaced and stuff, but right now it just all goes in here. There's this thing called type table, which is an array of something called struct type info, right? And those type infos, like I said, represent every possible type that can happen in your program. What is a type info? Well, it's a sort of a base class, derived class kind of thing. You could think about it that way if you're an object-oriented person, right? So the base just has this enum that tells us what kind of thing it is. This enum is not a complete description of the type. It's a general category, right? So integers, there's integers of different sizes, right? But they all kind of go in this category of integer, right? There's pointers to different types and stuff. There can be pointers can be SOA or not, but they're categorized as pointer or whatever, right? Arrays and whatnot. So what happens is you see something of this type in this type table, right? And then you can, based on what you see in this enum, you can cast it to one of these types below. So if you see integer in there, you can cast it to type in info integer and read out the rest of this information, right? So all of these guys, type info integer, float pointer, all are using this base, right? Which is like having it as an anonymous substruct or like inheriting from it if you're in an object-oriented language, right? So all that's saying is, okay, this type tag is at the beginning of everybody here, right? And then they supplement that with data that's specific to each particular type, right? So if you're an int or a float, you want to know how many bits that number is. If you're a pointer, you want to know what type it's a pointer to, and you want to know if it's SOA or not, right? If it's a procedure, you want to know the return type and the types of the arguments, etc. It's for every type, right? If it's a struct, you might want to know the name of the struct if it's named, right? And you might want to go look at all the members, right? And the members have names and their own types and their offset in the struct and all sorts of things. So you get really a great deal of information. Is this declared as constant, right? Is it imported by using all this stuff? And unlike some other languages that don't give you this kind of information at all, or that put it behind all sorts of weird barriers, this is right there in data structures for you to plow through as fast as you want. Right? So now that you've seen that, let's sort of go back and look at this, and maybe it makes more sense what this is a printout of, right? So when we got to number 15 here, that's pointer to U8, what happened was we got a type info, right? Because that's what we always get. And we read this value type, and we saw a pointer. It was 4. So when we saw that, we casted it to type info pointer, and then read out this type that it's a pointer to, and then printed it. And so if we go look at print types, that's exactly what it does, right? So remember, I've been blabbing for a couple minutes, but this print all types iterated over that type table and just called print type on every member. If you've missed the earlier episodes, this it and it index are implicit variables sort of declared by this iteration. It is basically visits every member of the array. So let's look at print type. And print type basically does what I just said. We take a type info parameter and then just this bool that helps me decide how to format things. Because, like I said, if you have a pointer to something or an array to something, I'm going to be calling this function recursively to print out the type that you're a pointer to and all that. And I'm deciding how much information to print based on whether we're top level or not. So once I get here, I'm using this type info enum, right? So I can refer to all these things without having to, specify them very specifically. And then I just basically do that casting I was talking about, right? If I see an integer in this type info, right? If I see that it's an integer, I cast it to this more specific type info integer, and then I print out things based on what it says, right? If it's a float, I print stuff out. If it's a procedure, I do something really elaborate. I cast it to procedure, I iterate over all the argument types, I recurse printing them out, and then I print this thing, and then I print the return type. So this syntax that I'm not printing out, that I'm printing out, is not quite the same syntax as in the actual language, because I didn't want to put that much work in. I just kind of spewed stuff out. But you actually, with a little bit of elbow grease, you can print back types in the same syntax that you read them in, right? And that means that you can use this facility to generate code. As always, all this stuff that I'm talking about works at compile time and at runtime, right? So you get all this type info at compile time no matter what. If you want to strip it for runtime, like I said, for the embedded systems case or whatever, you can, but you would still even get it at compile time to generate code with. And that can be very powerful. Anyway, so this is a big function that just, handles a bunch of cases. Let me go back to the bottom. So figure out how I'm going to do this. I'll do this. Sliding comments, and we'll run each piece in order. Okay. Let's run it again. So now we're just printing out types of a couple specific things, and then we've got some comparisons here. So let's look at that code specifically. Do type info. Here we've got a vector 2 and 2 vector 3s. Let's look. If you're not that familiar with games, these are not too surprising. Oh, this shouldn't be there. That's a spoiler for later. But we've got a vector 2 and a vector 3. That was a test thing that I put in that I never removed. All right. So those are just 2 floats and 3 floats. And we've got 1 vector 2 and 2 vector 3s. And there's this built-in function called type info, And you can pass type info any expression or any type, and it'll give you back that same kind of type info pointer that's in that global array that we were just printing out, right? So T1 is going to be the type info for vector 2. T2 and T3 are going to be the type infos for vector 3, because that's the types of these variables, right? So now we're printing type of v1, and then we're calling print type. Let me do this again, since I deleted the extra noise thing. Right, so type of v1 is vector 2, which, by the way, has these members at these byte offsets into the struct, right? Type of v2 is a vector 3, which, by the way, is all this stuff, right? Then we go down to compare these things, right? Is T1 equal to T2? No, because they're different pointers. But T2 is equal to T3. And that's an interesting property of these type info pointers, is that the compiler guarantees that they're unique. If two types are the same, even if they were declared in different parts of the program or something, you'll get the same pointer back. Which means you can test two types for equality if you want to. So T2 is equal to T3, T1 is not equal to T2. All right. Wait, I slide this down. I slide that down. Okay. Now, before you can already, from what I've shown, experienced programmers can see all the implications of what you can do with that. But I'm going to start off soft. I'm going to start off with some ways that this makes our life a little better before we even get crazy. So here's a function called simple any. Did I run it? No. So we just print some stuff. We print a float that's 1. We print a string, some other type, blah, blah, blah. So what does this do? We're declaring a float b. We're declaring a string c, declaring a vector 3d. We're passing them all to some function called print any, which we don't have, parameterized types or polymorphism or templates in this language yet. But what we do have is a type called any that you can implicitly cast anything to. And let me show you what any is. Over here, we're going to go back to that module. I actually, let me do it this side, just to be consistent about which file is in which pane. I brought this up in the right pane before. So an any is basically a small struct that has a type info pointer as the first member, and then a void pointer to whatever value you're talking about as the second member, right? Now, the compiler will implicitly cast anything to type any, right? And in doing so, it'll give you the type info pointer and the value pointer. So now you can make a function that takes anything, and this is like a more informative and type-safe version of a void pointer, right? So print any, again, I could have elaborated this function to handle oh, my webcam is kind of in the way. Let me shrink that. Sorry, guys. It's a little big. You don't need to see me that much. All right. So we have this type any, right, that anything will get implicitly cast to, and this function right now only handles 3 specific cases for the purposes of demos. And in fact, it doesn't even do that super well. Like if it gets a float, it casts to a pointer to a float. This is the default float, which is 32 bits, so you could actually pass a float 64 to here and it would do the wrong thing. This is not a very robust function, but it's for the purposes of the demo, right? And that is the thing that was printing these out, right? So this float colon whatever is printing that line, and this string colon high is printed by this line, and this, I guess I didn't do an integer. But I did a some other type, right? I passed a vector 3, and that's hitting this some other type, right? So I can pass any type into this function, and the function will just handle it, which is pretty nice. Yeah, I'll put it in the bottom. Since, like last demo, I seem to be at the top all the time, or I seem to have empty space at the top all the time. This time, I seem to have empty space at the bottom. Whatevs. Okay, so that's a simple version of any in function form. Now, you can declare a variable as any, right? Any is just a type. So here I'm saying there's a variable x. It's of type any, and we're going to assign it to 3.0. And I said before, remember, any is a type pointer and a void pointer to the value. The reason you have a pointer to the value is you don't know how big the value is. The value could be 1 byte, could be 1,000,000 bytes, right? And you don't want to try to pass 1,000,000 bytes on the stack or something. In cases like this, where this would be a literal that could be like baked straight into code, we actually ensure that this is on the stack so that you can take a pointer to it in cases like this. So here x is an any that's equal to 3, and now I'm doing a more inline version of what that function above was. I'm saying x is, and then I'm calling that print type function that printed everything, right? So x is an any, that's what print type is telling us. X.type, remember that the type was that type info pointer in the first slot of any, and we're calling print type on that, right? X.type is float32, because that's when you say 3.0, that's the default that you coerce to as a float32. And then if I want to print the value of it, right, I can cast that value pointer, which is a void pointer, I can cast it to a float pointer, right, and tell you what float it contains, and it's 3.0. Right? Now x is an any, so I can assign it to a totally different type. Right? Down here I can say, oh, it's a string, by the way. And let's print that. There's something subtle here, right? Which is when I call print any the second time, I'm passing an any argument, and any coerces to any as the identity, right? Like nothing happens. You could imagine some version of any that like wraps your any in another any, but that seemed like really bad news. So we can just call directly with an any. And then we can set y, another any, to the same thing as x, and we print that out, and that all works. So now, this level of introspection and manipulating like any kind of type and knowing what the type is usually the kind of thing that only happens in managed languages or very slow, high-level languages that have like runtime interpreters and stuff. But again, this is all like C-level code, right? There's a little bit of overhead involved in using an any, right? Because you're maybe taking something that is 1 register large, like a 3.0, and you're turning it into 2, right, by taking that pointer and stuff. But it's a relatively minimal overhead that gives you a great deal of power, especially when combined with these pre-baked type infos that land in your executable. Now, we also use this to do nicer, more type-safe varargs, variable argument functions, if you're not used to C++ or C terminology. So here's my variable argument test routine. Oh, let's run that. We'll look at what that means in a minute. So I've got some test procedure. It takes a string as the first argument, and args, which is variable arguments. In this language, I'm using 2 dots. Like in C or C++, you would use 3 dots to mean variable arguments, but same thing. So I'm passing a string as the first, and then anything else that gets passed to this gets piled into this args. And what args is, if you were to actually write it out, is it's an array of any, right? An unspecified length array. And so, but that because it's varargs, it collects all the arguments that you pass in. So basically, the arguments that you pass in get dropped into an array of type any, and then you can dereference that array, right? So because it's an array, we know how many items are in it. We can say args.count, right, and say, oh, there's this many arguments, along with this string. And then for every argument in that argument array, we can do something to it. So this function is just reporting which argument is a struct, right? So for every argument, it says, if this particular one is a struct, then print argument of that index is a struct. So that's what we're getting here. So down here we have A is an integer and B is a float, and C is hello sailor, and D is a vector 3, E is a pointer to a vector 2, and F is a flat vector 2 or value vector 2. And the first time we call this function, we say first with A, B, C, or D. Only D is a struct out of those. The rest of those are simpler values, right? So argument 5 is a struct, right? So the name is the first argument, 1, 2, 3, 4, 5, right? So that's D. When we call second, we're giving it 6 arguments, and 3, 5, and 6 are structs, right? That's 1, 3, D, D, and F, right? So that's obvious. And then third, we just pass a great deal of arguments just to show that this kind of thing works on a lot of stuff. We pass it a lot of E's and an F. And F is the only one of these that's a struct at all, and that's argument 20, right? So you can do varargs in a way that is much nicer than this C version, for example, and that you don't pay for very much. Now, this kind of varargs is slightly more expensive, probably. I mean, it depends on your platform and its calling convention and stuff. In C, you're basically just yanking stuff off the stack and arbitrarily casting it. And, that is fast, and it's also very, very dangerous, right? Like varargs functions are a pain in the ass. So we're being slightly more slow in that, again, we're turning everything into, well, if it was register size, we're turning it into 2 register sizes, right? And we're also adding this count. But those are very minimal overheads compared to the kinds of things that we're usually concerned about. And I made the trade-off in this case that with functions like varargs that are massively dangerous in languages like C and C++, that the trade-off was better in terms of giving you better ability to see what the hell is being passed to you, right? We'll see. We'll see if anyone complains about the speed of that. I don't think anyone will, because if you want to be fast, I don't think you use variable arguments, right? Variable arguments are for flexibility. So let's look at an example of that actually happening. So I've been using printf in most of these demos most of the time. But printf is dangerous, right? Because you have to specify the types of all your arguments in the format string, and then printf has to believe you about what those were, and you can crash if you get them wrong and all that stuff. Now, in earlier versions of this talk, I showed some check functions that you can do things like check dangerous calls like that. But another thing you can do is just change your function so that it's not dangerous anymore, right? So here's a version of printf called niceprint, where instead of saying %s and %d and all that, I just say % every time I want to insert something, and I put integers or strings depending on what I want to insert. This is a very low effort thing that I wrote in like 10 minutes, so it doesn't have format options and stuff. But you could put format options, and it would work just the same way, right? If I wanted like, %.3, then it could complain if I passed it something that decimal formatting doesn't apply to, right? So let's go look at, let me fight with the C++ formatting. It doesn't like my single quotes. Someday I'll do syntax formatting. Okay, so niceprint, just like that previous simple variable argument function, takes a string and an array of arguments. While the element of the string is not a %, we just copy it into this destination buffer. When we do hit a %, we want to pull another argument out of this varargs array. If we've got too many %, we can give a runtime error, like, hey, you didn't give enough arguments, right? We can also test that at compile time, like I was saying before, but in this case, you can also test it at runtime. We skip the %, and then based on what we got, I only handle 2 types here. I handle int and string. If it's an int, the way that I thought of converting an int to a string involved, modding by 10 and printing those out, which would give you the int in reverse order. Well, I check if it's 0. If it's 0 or 1, if it's 0, I just print 0, and if it's negative, I print the minus sign. And then I do this crazy thing where I reverse the thing numerically, where I mod it and then multiply a different number up by 10, and then I print that. So this is a totally goofball thing, but it prints out the number in the correct order. If it's a string, I just copy the string in there. And this is a very not good function because I don't check this buffer size or anything like that. It was just for the purposes of having a demonstration that you can have this very nice type-safe checking of things with very low overhead in a compiled language. right? With type introspection and all this stuff, right? So that's nice print. So now another thing that's annoying in languages like C and C++ is calling varargs functions with varargs. I think with variadic templates in C++, it gets a little nicer, but templates themselves are so horrible that I don't even ever want to be in that neighborhood. But the way that you call a varargs function from another one in C is like this very low-level annoying thing made up in the 70s, and it's horrible. Because, though, all our arguments are in an array, it's actually very easy. So I've got an example of that here. Oh, well, let me just... I never ran this last one. Let's just run it. I should run everything. So there we go. We had a 42, a max, and a 1394, and it's printing that correctly, as you would expect. All right. So now, second routine, printing some things. Let's look at what that does. We have this thing called first routine that takes variable arguments. And for the first n elements, which I've defined as 3, or if you give me less arguments than that, then n is less, I'm going to iterate over the first that many arguments and print them, right? And then I'm going to make this new argument array. And I'm going to bump the data pointer by n things, and I'm going to subtract n from the count. So I'm basically taking a subset of the first array, that's the, k minus n later elements, and I'm passing that to the second routine. And second routine just prints the rest of its arguments. Now when I pass it, I'm using this dot dot to say, hey, I'm giving you this array of any, and just make that be the varargs arguments, right? Like spread that into the varargs arguments. Don't make an array of one array of any, right? Which is a thing that you would get by default. It was an interesting choice to do this. My knee-jerk reaction when you were going to pass varargs to another function was like, oh, if it's an array of any, just treat that just like any, and just spread it, right? Just have that be the arguments. But that actually seemed like a mistake. Like it would be a weird semantic singularity in the language. It seems better if your variable argument function gives you what you passed it, unless you say spread. So in this case, I'm spreading this array to second routine, and second routine prints out what we have. And this is very fast, and very reliable and very easy. You don't have to do any weird system-defined macros or anything like that. So anyway, we passed first routine these 7 things, and you would expect it to print 3, and then pass the other 4 to second routine. And that's what happens. 1, 2, 3, and then second routine 4, 5, 6, 7. And then, down here, I'm just passing 2 things. These 2 are just more like testing robustness of the fact that this is an array of fewer things than you expected, right? So here's 2 things, and first routine correctly cuts down how many it prints to 2. And then the third time, we call it with no arguments, and we print nothing, because this array ends up having 0 elements. And so we do this for loop, and then that for loop, and they both have 0 elements. So that's all good. So, wow, we might finish on time today. Now, you don't have to start with variable arguments in an array. You can start with any array. So here, I'm going to make an array of things and pass it to a variable arguments function, right? So let's say n is a constant 5, and a is 5 any's in an array, right? The first any is a string, the second is an integer, the third is a pointer to a vector 3 allocated on the heap. The fourth is a pointer to this print type function that we started this session off with, right? When we were printing all the types in the program, right? And then the fourth is is an array of 2,000 functions taking in float parameter, an int parameter, and a string, and returning a vector 2, right? These are all totally valid things to put into an any. Oh, and it's a new array of 2,000 things on the heap, right? So that's all totally valid. And we're just going to print any on all of those. Remember, print any wasn't our print type thing. It was the simpler one. So it's going to Let's show what this prints. It'll print some other type if it's not a string or an integer, basically. So we're going to then, just like I was calling another varargs function, we're going to spread this array into the variable arguments, right? So I'm printing all the items in A first as an array, and second as actual variable arguments, right? So here I'm pulling some things out of the array and adding some things. I'm calling the same function both times, print items, right, which is right here. So that shows a little bit of the versatility you have when you have this spreading arguments into a thing. So, in the first call, I've got 5 items, hello 42, and then the last 3 are other types that we didn't want to print out, right? And then the second array has 6, right, because it was A of 0, 1, 2, 3, and then this 15 and done. And we say 0, 1 is a string and 42 again, 2 and 3 are other types, and then 15 and done. Ta-da! And again, because these are any's, they get passed directly. They don't get wrapped in another any, because that would be a disaster. Which is interesting because, again, that's a little bit different from the decision that I made that an array of any doesn't get wrapped. But if you think about it, they feel like really different cases, actually. All right. What did I mean by that? Minor implicit conversion happens. I don't think any implicit. What did I mean by that? Oh, right. There is an implicit conversion here in that, a variable argument function, remember, like I said, is an array of unknown length of any, right? And anytime in the language you could have an array of something, right? And you can pass that, and there's an implicit conversion that converts it to something of unknown type. And this is just to say that that happens, here as well. Like, just because it's variable arguments doesn't mean that that kind of thing breaks. Like, that still works. Okay. Which, by the way, if that seems weird, all that is it's like in C where you might have a pointer to any, but it's also got a length, right? So just like in C, you have an array of 100 things, and you can pass that to a function, and it gets converted to a pointer, and you lose the length information. Here, you keep the length information, and you can query for it. It's analogous to the thing that happens in C. It's just got a little more information. All right. So now let's talk about embedded systems, or what if you don't want this information in your program. And actually, most of the stuff that I've shown so far actually works, or a lot of it still works. What happens on an embedded system, right, is you can set this variable. There's a build setting. Remember, you can set all your build settings. I'll answer that question after the thing. You can set all your build settings from your own compile time program, right? And one of those build settings, is this Boolean runtime storage list type info. And if you set this to true, you're basically saying, I don't want all that data for whatever reason. Don't give me that data. But you still can use type info. And what happens, you still get back a type info pointer, because I didn't want to force you to rewrite your program or anything. It's just that pointer, instead of pointing to valid memory with this description of your type, now there's no storage to store that. So what it is just an integer describing the type, right? You get a unique integer that's actually the same index into the array that it would have been if the data were there, right? So remember this example where we had vector 3s and we were comparing the types. You can still do that. And let me compare this to the version from before. So we had this print any. Wait, where was my? Yeah. Okay. So let's look at this first. So we've got our T1, T2, T3, and we're assigning them, and then we're printing them out down here. Ignore all these print statements in the middle, because we didn't bother to do those this time. We're doing the same thing, and we're printing out the same predicates, and it still works, right? So our output now is T1 is not equal to T2, right? But T2 is equal to T3. Now we've got print any. Now I wish I had more columns. But if I line these up next to each other, sorry about all the word wrap, what you'll see is that in the old one, I was actually dereferencing the type info to get at this enum, right? Now you can't dereference the pointer because there's no storage, but you can, on the right, just say type info of float, right? Or type info of int, or type info of string. And again, you could get more specific. You could say type info of float 64, or of, S8, signed 8-bit integer, or anything like that, and all that works. You could do type info of vector 3, right? Because remember, every type has its own unique element in that table, and what you're getting now is the same integer from the table. So all those kind of tricks still work, and you can still do all the print any stuff, for example. So here's my same code that we did in simple any. Now here doing it again with the embedded systems version, and it works as long as I don't use the dereference thing. As long as I don't try to dereference the pointer, because it's not a really real pointer to memory. Now I can't then go and print out that detailed type information that I did at the beginning of the demo, right? Because it doesn't exist. But you do get sort of the type of the root type, or the top level type of whatever you pass to type info here. So here I call print all, and this is just to demonstrate that this also works for varargs, right? So I've got a float, a string, and a vector 3, and I'm saying print all on all 3 of those arguments, and I'm passing those to print any, and blah, blah, blah. So that's this last float, string, and vector 3. So on embedded systems, at no runtime cost, you get a great deal more power than you get in C or even C++ in terms of what you can do at runtime. Or at compile time, right? Because remember, anything that works at runtime works at compile time. All right. Just as a minor note, there's no code for this next one. But this is just a reminder to say that check calls, if you remember the first demo that I gave, I was checking functions like printf by designating a check function that ran at compile time to validate the arguments to that function. And at that time, there were like a lot of weird arguments to it because we didn't have this kind of expressivity about what the type is. But now it can be much simpler, right? So now if I was going to check printf, I can just have my arguments be an array of any, just like for the varargs functions, right? And then file and line number. Very simple, right? And you can check the arguments. And in fact, in the invaders program, it's been converted to do that, right? So here's the check printf that's actually running in the invaders program, and it's got all that code to like validate the printf arguments. And it looks at an array of any and a string and an int. So that is all very nice and a very practical use of the any type. All right. Now let's start getting down to business, because all that was kind of introductory stuff. Someone's asking what would happen if I tried to print out that detailed info. What would happen is you'd be dereferencing a pointer that probably doesn't point to valid memory, so you would you'd crash. You get some kind of runtime exception, just like dereferencing a null pointer, basically, but slightly non-null pointer. Okay, field by name. This is where we start having fun. Now again, everything I'm about to show works at compile time or runtime. Remember, I had all that detailed information, right? Not just what type it is, but like if it's a struct, what are the names of the fields? That's actually something you want to know all the time when you're programming, especially programming games or any kind of application, right? So here I've written a function where I pass it in any, which in this case I want to be a struct, right? So I'm going to pass the name just for printing debugging purposes, but I'm going to pass a struct, and First, I'm going to validate that it's a struct. And if it's not, I'm just going to give you an error. I'm going to printf an error. You'd probably want to actually return an error code or something, right? So now we're doing something a little bit like what you would do with templates in C++, but without templates, right? This is just straight up code. Now, I've got an info struct, right, which is casting that. Now that I know that what's in the type tag is struct, I can do what we did at the very beginning of the program and cast that to this type info struct subclass or substruct. Let's go look at, again, what that looks like. So we have type info struct, and it gives you a name and then an array of members, type info struct member, right? And that's this thing right here, which gives you the name of the member, pointer to its type, where it is in the struct, some flags like is it constant or imported, and some notes, which we'll talk about later. So now I'm casting to that because I know that's what it is. And then for every member in this array, right? Sorry, this isn't a debug name. This is, I explained this wrong. So I'm passing a struct and the name of the field that I want to extract from the struct. Right? Wow. Yeah. Why did I get that so wrong in the initial explanation? Anyway, so we search through each field, and if the strings match, then we take that value pointer, which is the base of the struct, we cast it to unsigned 8-bit, which is like unsigned char if you're in C. And then we add the offset in bytes of the field, right, of that member, which gives us a pointer to that member of the struct. And then we return that pointer up here, right? We return a pointer to U8. And if we didn't find it, then we say, hey, we didn't find it, and we return null, right? So down here, I've got a vector3. I'm going to assign it some default values, and I'm going to make a string y, and I'm going to say, give me that field, and then print out what we got back, right? So let's do that, right? So the y coordinate is 4.0, right? This function successfully iterated through the struct members, found the slot labeled y, gave me back. Now remember, okay, this is a compiled language. So we're not doing what we would do in like a Lispy language or something where different languages are different, right? But a lot of very squishy languages store structs as basically the name of the field and the value all together all the time, right? We don't store the name in this language, right? It's like C. It's just values packed into memory. But this metadata that's available to us gives us a mapping for everything of that type from the name to the pointer, right? And we're using that. So we're getting the field called y, and we're printing out the value, right? Now, if we look for a field called hello, vector3 doesn't have a hello. So what happens is, hey, field hello not found, right? That's this printf up here. And we could try to call this function on 3, right? 3 is not a struct. So what's going to happen is any.type is going to be integer, not struct. So that first argument happens, and indeed it does. Or first error happens. Argument is not a struct. So that's all cool. And that functionality suddenly, as soon as you can do that, gets rid of a great deal of pain that we all currently suffer in C++ in game development. Whenever we want to interface with a high-level language, for example, like if you've got a scripting language running on top, you always need to communicate back and forth, which often involves exposing data structures to the scripting language. And right now, what we typically do is we have a lot of ugly macros that we have to go update. Like every time we add something new to the data structure, we better remember to go change the macros or you'll have a problem. Or, you might have some preprocessor that tries to like parse your header file and whatever, right? So instead of doing all that stuff, you can just, at compile time, you can use this kind of facility to generate a serialization or exposure function that'll tell your higher level language how to access your struct members, right? Or You can look them up at runtime. This particular function that I wrote here that searches linearly through the thing is sort of the slowest version, right? Because you don't want to, like every time you want to query for a member, you don't want to go back. But you could use this to build a table, right? Or to generate some code at compile time that you then call at runtime. So I've said serialization a few times, so I wanted to build a specific serialization demo. So let's do that. Serialization. Whoops, what am I doing? All right. Serialize simple. So let's say you've got something that has state that you want to save, right? Like a font. I'm writing an editor maybe, and I've got a font that's your current one, and I want you to be able to restart the editor later and have the same font. So I want to save this. And so what might it have? Well, it might have a name and a point size and a weight, and maybe it's italic or underlined or not, right? So I'm going to make two instances of this struct, A and B. A, I'm not doing anything with, so it's going to keep all the default values that you see up here. B, I'm going to change. I'm going to say, oh, B, instead of inconsolata, I want anonymous pro, I want it italic, and I want it big. So let's multiply the point size by 2, and we're going to serialize. So I've made a serialize function, whereas the earlier functions that we've looked at just printf stuff right to the console. This one is building a string and returning us a string. So we're getting a string s, right? We're printing it out, and then we're freeing it. And by the way, all the string manipulations so far and that we're going to look at now are being done with strings basically the same as they are in C. So like a pointer to array of unsigned character, or a pointer to unsigned character, right, which is of unknown length, and you have to know the length by finding the 0 at the end, right? I don't think that's such a good idea necessarily. And so later on, the language is going to have, strings that are nicer to deal with than that. But in the meantime, I can't write everything at once. So we're going to be doing lots of zero-terminated string stuff like you would in C. Is not my recommendation. So anyway, so serialize. Whoops. So that's a function that takes in any and returns a pointer to U8. And again, we insist that it's a struct. So if it's not a struct, we return a runtime error. We get that type info struct. We iterate over the members. Let's ignore this thing for a minute. And, based on, we do the same thing that we've looked at a few times. Based on the type, we do different stuff. Instead of printf, I'm using this thing mprintf, which is a relatively inefficient way of making a string in memory, right? If you were trying to make a really fast serializer, you'd have like a memory buffer that you were being very efficient about how you wrote things into. It's not what I'm doing here. So I'm putting the name and then the value. Let me go one field. I'm putting the name and then the value into all this stuff. And then, like we've seen, I'm casting to a pointer to what I know it to be, and then dereferencing that, right? If it's a string, it could be a null pointer, in which case I just write out a dot so that I know when reading it back in that it's null. Otherwise, I write out the whole string. This is a very simple version of a serialization, but it's an analogy to what you would do in a production environment. You would actually have a function that looks like this. It just does a much more hardcore job. Like it probably writes things out in binary and without the names and all that good stuff. Okay, so I'm iterating over all the members, and I'm doing this super lazy like string doubling thing to concatenate to my result. Don't ever do that in a production program. I'm freeing the old thing and whatever, and then I'm returning the string. So let's just look at that so far, what the output of that looks like, right? So here's font A. Oh, I forgot to mention, when I'm outputting a string, I don't just output the string itself, but I also output this length, right? I'm taking the length of the string and putting it first. And that's because when you're reading stuff back in, like when you're serializing, usually your preference is not human readability. Sometimes it is. But usually it's clean code and fast loading, because you want your app to start up fast. Especially, in the witness, I just called the witness an app. I feel so dirty. It's not an app. You want your program to start up fast. In the witness, we load a lot of data, like some large subset of 3 gigabytes of data, and we start up actually pretty fast considering. Start up way faster than Photoshop, for example, right? And why is that? Well, because we care. So yeah, I'm saying how long the string is so that you can make sure that you're ready to put it in some memory before you have to read it, right? So you know how much space it's going to take. Point size and integers and stuff and booleans I just write out in a more straightforward way. So here's our font A and here's our font B, and they're both what you would expect, right? Except again, I'm building a string instead of printfing it directly, and then I'm printfing the string when we return. Okay, so oh, that's the wrong function. I'm spoilering. Okay. Then I have a font C, and font C has the default settings. And I'm going to print out a before and after. So when I first instantiate font setting C, it's going to have all these default settings the same as A, right? But I'm going to unserialize from this string that we just got from B, right? So S comes from B. Now we're going to unserialize S into C, and then we're going to print the values again. And spoiler, it works, right? So before, font C's name is Inconsolata, and it's 20, and after, it's Anonymous Pro, and it's 40. And we'll look at the unserialized function. And again, it's the same thing. It's like we take an any and an input of bytes. We make sure our any is a struct, and then we start iterating over all the members of the struct. Or no, I'm doing the opposite way, actually. This is not the production quality direction that you would do it, because like I said, in production, you probably wouldn't have names. But here I parse out the name, and then I find that name in this members array, again, very slowly, like I don't make a table. But then based on what type it is, I like scanf that type and whatever, right? If it's a string, I like allocate a string out and poke it in. So I unserialize this data structure from that string and then free the string, right? So here's the minor philosophical issue that I want to talk about, which is in the language so far, we don't have const as a modifier on pointers, and we don't have references because references don't mean anything. Like a reference is a pointer. So it's an absurd complication that got added to C++ for no good reason. What do we do? Well, we have this interesting emergent result that, remember, in any gives you the value by giving you a pointer to the value, right? And by taking a pointer to the value, it looks like we're passing something by value, but really it's getting coerced into something that has a pointer. And I'm not sure how I feel about that. Maybe it means we need const pointers. Maybe it means something else. But right now, what it means is if you pass something to a function that takes a type any, that thing can be modified currently. And I'm not sure how I feel about that. And I just wanted to make that explicit. Okay, but so we wrote that big serialized and unserialized function. And the nice thing is, now that we can introspect, right, we can turn around and use that same code with 0 modifications on a completely unrelated data structure, right? That's the whole point. So I've got this physics tweak structure where we've got gravity and friction and a time step, and I've got an instance of it. It's going to have all these default values. I'm going to serialize that into this string s2. I'll free it later when I'm done with it. And then I'm going to print out that struct using the same serialized function, right? So that's this part down here, a different struct using the same serialized function. Gravity is minus 9.8. Friction is 0.29, time step is 1.6667, and just to, or 0.016667. And just to show that this is working, I'm just going to very cheekily modify the string that we got. So we serialized into a string. Now I'm going to change every 9 in the string into a 5, right? Every character 9 gets turned into the character 5 by this loop. And then I'm going to unserialize it, right? And we successfully parse the string because gravity gets turned from minus 9.8 into minus 5.8 and friction from 0.29 to 0.25. So that all works. We turned around, we used this serialization code on a completely unrelated data type, and we didn't need to do anything squishy and high level to do it, right? We just needed compiler help in the right one or two little spots. That's sort of the theme of this episode. Now let's talk about notes, which is possibly my favorite part of all of this. Now I've got a similar situation where I've got font settings, but included in this struct is maybe stuff that I don't want to serialize. Like maybe I've got some debug info that I don't want written to the file. I've got like a value that I'm using for my hash table that might be system dependent or whatever. Like sometimes there's just things you don't want to serialize. And back in the version of life where you used macros to designate these, the information about what you want to serialize or don't serialize was stored far away from the struct itself. So you had this place where there's different far away parts of your code talking about the same thing that's important. Like when you're reading the description of this structure, you want to know what is ephemeral and what is recorded, right? It's very important. So here I've got this @ notation where you can put an @ and then any string, and up until white space, all this gets put into one thing called a note. Now, if you saw one of the first talks before there was even a compiler, when I was just talking about ideas, I floated this kind of syntax for telling the compiler to do certain stuff with your data structure. That's actually not what's going on now. So this is a little bit different. What's going on now is purely for you as the user. So this no serialize is not something the compiler knows what it means. Compiler has no idea what, it's just an opaque string. No serialize is something that I made for my own code to interpret, right? And so if you go back to this part, remember I said ignore this line. The same serialize function that I had right now, while it's iterating over the members, if it sees this note on a member called no serialize, then it'll just continue through the loop and not bother, right? And so let's go look at hasNote. It's a very simple function where we just say, hey, we take a struct member and the name, right? I don't know why. This is the name of the note. I guess I should have called it note name or something. We take the struct name member and the note that we're looking for, and we say true or false if we find it, and we just look in this array of notes on the member and see if the name matches. So again, this is not written for speed, it's written for simplicity. You can make your own version that's arbitrarily fast. So again, that's this notes array that's in the struct member in BASIC. So I could put anything here. I could put like I love Taylor Swift or something, but not the music one, the Swift on security one. I don't know. I can put anything there. We'll show in a little bit an example of something more intricate. But so for now, if this is working, then when we serialize and print it out, we shouldn't get those two fields, right? And in fact, we won't. So we have font name, we're skipping debug name, and we go straight to point size, weight, is italic, is underlined, and we're skipping internal hash value, right? So that's cool. Now, what could you use this for? Well, anything. The idea is it's a completely user-defined thing that you can use to interface your program with other stuff. For example, in the witness, we have an in-game editor that we use to build the world. And you might tag some fields of some structs as like, don't put this in the UI because this isn't something that we want to be user changeable. Maybe it'll get serialized, but just don't display it, right? You could say things like UI major, like we want this to be big on the screen or we want it to be small on the screen. Maybe for the debugger, oh by the way, I should point out this notes aren't just for struct members. They can go on any declaration. So if you have a function like, I don't know, like, if you have a function, you can put a note here or here. I felt like it was syntactically better to put the note in the header of the function. And similarly on a struct. So you can say struct, hello, sailor, right? Or you can put it for consistency trailing the declaration, right? So any declaration, you can say n is a constant 3. By the way, oh, I guess you put the semicolon, then you say hi mom, right? So that all works. Of course, there's no way to read that note right now because I don't. Yeah, it's a minor thing. You'll be able to. Let me go back to where we were. So say you want to interface with your debugger, and your debugger is aware of these notes. You know how you have those little pissant functions that are just like little helpers, and you don't ever want to step into them because they like iterate over some hash table, or they create a vector3 from some floats or something. Just tag that as no step, and if your debugger pays attention to you, it'll just step over it, right? Maybe you want to designate some things about how stuff gets serialized. So, hey, this float gets serialized, but it gets serialized as half precision, so it's 16 bits, right? Or it gets quantized to a value from 0 to 9, right? 10 different stop settings. Again, those kind of things are very important for you to know if you're looking at the struct definition trying to understand it, right? And now instead of having those only live way off in the serializer and be hard to remember and hard to understand, now you can, if you want to, put them right there on your struct. And I think that's very powerful. So now, as I've been saying before, I'm not going to actually run this one because I didn't want to write the full parser for all this stuff. But like I've been saying, in a production system for a game or something else, you probably want to serialize things in a very efficient way. So you're packing binary data structures, and you don't want to store all the names for things because that's very redundant and slow, and it confuses the issue when you're parsing. You want to just store the version of the thing and know based on the version what the names were, or what the slots were, and what the types were. So then you can just crank in the binary data. So instead of reading character name string, class name string, health max U32, you just ignore all this stuff on the left, and you load string, U32, U32, int, U32, right? The problem with that is, of course, during development, your data structures change over time. And your serializer has to deal with that if it wants to be backward compatible, which it really should be if you're not going to go completely crazy. So what I can do is I can tag this struct as a certain version, right? It's version 8 right now, and maybe if I went and put a string called blah that says hi mom, right? Then I would upgrade it to version 9. Again, if I forget to do that, then my program hopefully will complain. And you could make a compile time facility, like it might complain at runtime by crashing, like, oh, this doesn't match what I thought. But you could make a compile time facility that iterates over these members and builds a hash code out of them and stores that in a little file database, and then looks it up every compile and makes sure it's still intact, right? That I should have actually done that as a demo here. I didn't think of it. Sorry. That would have been an awesome demo. Maybe I'll do that next time, just as a little teaser or chaser or something. That's a bummer because I was thinking about something to do like at a very specifically compile time thing that doesn't make sense at runtime, and that would have been it. Okay. Anyway, so I can upgrade the version on it. Whoops, I didn't want to delete that. I upgrade the version on it anytime I do something. And then as I deprecate items or add new items, I can tag them with when they showed up. So when I first started building this game, characters didn't have experience. But when this was version 6, I added experience, right? And so now my parser needs to know if I'm reading this binary data out of a file, if it's 5 or earlier, don't try to read this U32 because it doesn't exist. But if it's 6 or later, add that, right? And then sometimes later you delete things. So like, oh, I had this inventory where I have an active item, but after version 3, I stored this somewhere else in a different data structure. So take it out of this data structure, but I can still load old save games and stuff, right? And I can still talk to old servers over the network or old clients or whatever, right? All of this stuff pertains to networking just as readily as to files. So, you know, this says this is valid from versions 1 to 3, right? And member flags is valid from versions 5 to 7. And I didn't actually write the code to parse these out, but given the examples that you've seen already, it is very straightforward. You look for the note, you like see if it starts with the letter V and then a number, and then you parse out this thing afterward to decide what to do. And preferably you do this at startup or at compile time so that you have a little table that tells you exactly what to do when you see a party member in a file. Now, the annoying thing about this is, you know, let's say we keep doing stuff and we get to like version 178 and we have all kinds of deprecated stuff. Imagine that these are different members with different names, and I didn't just paste the whole same stuff. These guys, I'm paying for these guys with memory still, right? Like these are still members of this struct and they still exist. Like this note that says it's only from version 1 to 3 is just a note. Like I said, the compiler doesn't know anything about what that's supposed to mean. So at some point, I still want to be able to load old versions, but still have an optimized version of this that like doesn't have these things, right? I want to eradicate those from my code. And the way you can do that is like this. What was I doing? All right. So let's say down here, here's my version 7. I've got all this messy stuff. And when I want to clean out the I don't know why this line was here, right? Anyway, when I want to clean out the code, I can delete this stuff and put it in this old struct, right? And point to that. So I'm saying, oh, I did it. Sorry, I was reading it backwards. I was like, this doesn't make any sense. God, this is a mess. I better not check this in. Anyway, so here's what this is the new one. Sorry, I thought this was the old one because it was higher. And here's what I'm saying is, remember everything from the @ sign to white space. I suppose that's dangerous in this case because if you forget the white space, your brace ends up there, but you'd get a parse error down here. And this syntax, by the way, is provisional. So if we find something that we like better, it's very easy to switch. But so, you know, the note that gets attached to this struct is all this, right? So we say it's version 8. And by the way, the slash means, oh, there's an old version called party member old. Party member old is going to be something that my game doesn't ever instantiate. So however much stuff in it doesn't matter. But it's still living in that type table. Because remember, that type table has everything in the program. So in that type table, I've got all these old members and what type they are, which is all I need to load them correctly, right? And what versions they existed. So I could delete this v6, and I've already deleted this 1 to 3 and 5 to 7, right? So I'm running efficiently with this, and if I hit like a version 5 entity when I'm loading data from a file or over the network, I can refer to this old version that has all the previous history, right? And that's nice. It's very compact and very nice, and it talks in the same language as the rest of the language, right? If I want to know what the history of this data structure was, I don't have to look at some weird macro language that I made up in one of my files somewhere and like try to translate what that means in terms of the types, right? I know exactly what it means because these are the same declarations that I used back when the program was running. So that is the demo for today. I want to reiterate all the stuff I've shown today it's the kind of thing that you usually see in squishier languages. You get limited facilities like this in languages like D or Rust or things like that. But I'm not aware of any other language that gives you totally free fire access to all the real data that you want and lets you wander among it as you want. So remember, all this stuff happens just by, there's an array of these type info things, and you browse the array at will. And you can process this data. You can store it into any other format that you want. You can do it at compile time. You can do it at runtime. It's all good. OK, that's the official presentation. So I'm going to take a few minutes break, and then I'll be back to answer questions about this stuff. Back in 5 minutes, people. Yeah, I don't know C# reflection very well, so I can't comment on it. But C# is a managed language, and so it's a lot squishier than what we're talking about. What what I really mean to say is that this is a very, very minimal overhead thing, right? It's a small amount of data in your data segment, and or if you want to use the any type or variable argument functions, a very small amount of overhead there, and you get a great deal of power for either of those things. Much more, I think, than in most languages that are trying to be purely compiled, fast languages.